So welcome, Marco and Maria. Now we have the presentation of Marco Schreyer that you have here, the title in the presentation. Marco is a PhD candidate in computer science at the University of St. Gallen in Switzerland, he works in the Artificial Intelligence and Machine Learning Research Group and has been a visiting researcher at Rutgers Business School Continuous Auditing and Reporting Lab. His research focuses on the application of deep learning techniques in accounting and auditing, and previously he worked for PricewaterhouseCoopers Forensic Data Analytics for almost 10 years. So the floor is yours.
Yeah, thank you very much. Thanks, Sonia. Maybe let me also start very briefly with a thank you to Enrique and Manuel for organizing this wonderful event. It's really a pleasure of being here and bringing all these people together. Also yesterday evening, I think we had a wonderful dinner in the city center of Madrid, and yeah, it was fantastic to have been part of this group. Yeah, as Sonia said, my name is Marco. I'm a PhD student, and I had the wonderful pleasure over the last 9 months to stay with the Rutgers group in New York and conduct some research on the intersection of deep learning and continuous auditing. And when I submitted a paper to this conference here, I think the world was a little bit different. It was, I think, to a certain extent before ChatGPT came around. And that actually motivated me to a certain extent to yesterday night, after we had these wonderful discussions in Madrid, maybe to change a little bit of the slide deck. So please forgive me if some of the slides look a little bit maybe uglier than they usually should look, because it was on a very short notice. What I want to speak about today is really maybe an endeavor that we started 9 months ago when I came to Rutgers, and really the idea of, okay, how can we improve continuous auditing, continuous assurance, or continuous intervention in this age of deep learning models? That's what we thought about when I was there. And I want to very briefly start with a small taxonomy about artificial intelligence, because I think it's a term used a lot these days. And I think it's maybe good that we have a common ground or common understanding, or at least for the talk that I'm presenting. So we know that artificial intelligence is an umbrella term for a lot of different tools and techniques that have been developed, right? I mean, we have expert systems, we have approaches for knowledge representation. But one driving momentum these days is the subfield of machine learning, where the idea is basically that we train machine learning models, and hopefully, or eventually at a certain point in time, these models will be able to do similar tasks as we humans without explicitly programming them. So that's the vision. And a subfield of deep learning, a subfield of machine learning that is gaining quite some momentum and really is probably responsible for all the breakthroughs that we see over the last couple of years, is the subfield of deep learning, where we train these large neural networks, and these neural networks are actually able to learn or extract features from the raw data itself, rather than having humans extracting those features. So if you think about a deep learning process in comparison to a machine learning process, what you have is you have this concept of so-called end-to-end learning, right? While in classical machine learning, we still have a human in the loop that performs the feature extraction of a particular data modality or of a particular data piece. And these features are then fed into a classifier or a machine learning algorithm, for example, like a neural network. And hopefully over time, with enough training data, the neural network will be able or capable of accomplish a certain task. In deep learning, what we are trying to achieve, and quite successfully over the last couple of years, we want to get rid of this human intervention. And it turns out that the deep neural network architectures are actually able to extract or learn the features itself, and at the same time also are capable of maybe fulfilling a certain downstream task like classifying images. And for example, in this instance, we see maybe if there's a bird in an image or not. So that's the idea. That's the idea of end-to-end feature learning. And this has been quite successful over the last couple of years, and it has been also quite successful in the audit domain. I mean, there have been quite some publications in that domain where deep learning models have been trained, for example, for financial fraud detection or for audit sampling. Interestingly, and we know our profession is a little bit, or can't keep up with the high velocity that we have in computer science research, usually these publications are not published in accounting journals because the review process usually takes a little bit longer. But as we see in computer science, there's this high velocity of this research. And then I think since 2 years or 3 years ago, there's a new, you can basically say a trend in the deep learning community, or maybe there's a new animal in that field, and that's the idea of so-called foundational models. And that's quite interesting. This is really, I think, a new paradigm shift even in the deep learning space. And foundational models, I mean, the term foundational models has been originally coined by the Stanford University and the Center on Research of Foundational Models. And these are large-scale models trained on a vast quantity of data that can be adapted to a wide range of downstream tasks. So this paper was published 2022, so 2 years ago. And the idea of this foundational models is basically that we can learn large or deep neural networks based on a lot of different data modalities, like we see here, for example, text, images, speech, structured data. And once we have learned this large model, for example, a large language model like GPT or a BERT model, for example, then we can use this model with all the knowledge that it has accumulated throughout the training process from all these different data modalities and fine-tune it to a downstream task, like, for example, question answering, sentiment analysis, and all those other things. What's new with ChatGPT is that this fine-tuning process can now be done with natural language, and that's quite exciting. That's why we are so excited about this technology that we see these days. But the underlying model of GPT, of a ChatGPT is, for example, a GPT-3 or a GPT-4 model, which is one of those large language models. And they have been around already for quite some years. For example, GPT-1 was published in the deep learning space in 2019, but over the years they become more and more powerful, and with the reinforcement learning-based human fine-tuning, we are now capable actually to fine-tune them via natural language. So this is a quite exciting time that we are witnessing nowadays. We also see, I mean, with the emergence of foundational models, that there are more and more foundational models published. For example, I think it was just a few weeks ago where Bloomberg also trained a large language model based on all the data that they have, for example, in-house. So this is, for example, we see more and more also this specialization of these foundational models or these large language models. For example, Bloomberg here trained Bloomberg GPT, and this is a model that consists of 40 billion parameters that are trained, right? Accumulating all the knowledge, or a lot of the knowledge that they probably have in-house. So quite exciting times, because once we have trained such a model, we can use it for a lot of different, or Bloomberg can use it for a lot of different downstream tasks. Another thing that we also see, and a little bit of a different direction of these foundational models, is, for example, a publication that was published 2022, also just 1 year ago, by the researchers of Google DeepMind. And they trained a deep neural network, which they named Gato. And this network is actually able, or this large foundational model is actually able to accomplish more than 600 different tasks. So basically, we see this idea of multitask learning in the sphere of these large foundational models. So neural networks are now trained in a way that they are not only accomplishing a single task, a highly expert task, so it's more like we want to train these general purpose models. And this was actually the starting point for a lot of thoughts that we had at Rutgers at that point in time, because we saw these limitations, right, where a majority of the deep learning-based audit models that we saw until that point in time emerging have been trained on single client data very often, maybe for a single time period, and then also for a single audit task. So this was one of the challenges. And we asked ourselves, okay, why is that the case? Maybe we can do something about this or improve this. And we developed ideas along 3 different branches or 3 different lines of research, and they all luckily resulted in publications. And what I want to show you is a little bit an overview of all the things that we did at Rutgers. So the first thing that we asked ourselves, okay, can we do something in the area of single task learning and enhance these models that we have towards multitask learning? So we developed an idea using self-supervised learning techniques, which is a highly specialized architecture for general purpose model training, so that we are able to train a model that is trained on journal entry data, journal entry accounting data. And once we have trained this model, we want to fine-tune it to specific downstream audit tasks. Because what we want to avoid is really, we don't want to avoid in an audit context, or what we don't want to do is we don't want to train always for a specific audit task a single model. Preferably we have one model as auditors, and we can use this model and fine-tune it to different audit tasks. And this worked quite well. So here's, for example, just a visualization of the results that just a single model gave us. So we trained this model using journal entry data, was a couple of million journal entry records. And it learned quite nicely, for example, to disentangle as a first task the generative processes that the underlying data was comprised of. And at the same time, we could use the same model to detect accounting anomalies, for example, as we see here in the latent space of the autoencoder neural network that we trained. And the third audit task that we also wanted to learn in parallel was actually learning representative audit samples. Basically saying, okay, model, so that we can ask the model, please provide us a representative audit sample based on the representations that you have been able to learn. So this was a first baby step towards the direction maybe of multitask learning using self-supervised learning, so that we are training a model that can accomplish a variety of different tasks. Another thing that we are also quite interested in when training these deep neural networks or these models is the idea of continual deep learning. So if you've trained, for example, a neural network, what happens over time, because these deep neural network architectures, they have to a certain extent a similar behavior as we humans. For example, if we train it on a stream of data and the data comes in throughout the training process, what happens over time is that these models start to forget. For example, to accomplish a task that they have been trained on maybe a couple of audit periods ago, right? And this phenomena is called catastrophic forgetting. And this is quite severe. So it could be the case that, for example, a model that was trained to detect anomalies in audit periods a couple of audit periods ago won't be able to do this 10 audit periods from the initial training audit period, right? Because we have this distribution shift in the data that we see over time. So this was another thing that we worked on as part of the endeavor that we started at Rutgers. So we really trained these deep neural networks with certain techniques from the continual learning space, for example, experience replay or elastic weight consolidation, in order to overcome this challenge of catastrophic forgetting. So that these distribution shifts in a continuous auditing setting won't actually affect the performance of the model, for example, in terms of anomaly detection. And once we applied those individual continual learning strategies in this training of these models, it was quite exciting for us to see that, the fraud detection or anomaly detection capabilities of the models could be preserved while training it over different time periods. So this helped us, especially in a continuous assurance or a continuous audit setting, to reduce the number of false positive alerts that usually just have been created because of the distribution shifts in the data quite significantly. And that's what we see here. Another thing that we were also interested in is the so-called federated learning of deep audit models. And this is driven by the idea that usually what we have in an audit setting is, and when I was working, for example, at PwC, we usually audit clients or similar clients that are operating in the same industry, right? And so as auditors over time in our profession, what's happening is we are starting to specialize in a particular industry. But the challenge is that nowadays, especially with the data privacy or data confidentiality regulations, we are usually, to a certain extent, not allowed maybe to use a model that we have trained on the data set of a particular client and take it to another client, because there could maybe this violation of data privacy or data confidentiality, right? But one approach to this, in order to train deep learning models from different clients in a privacy-preserving manner, is this idea of federated deep learning. And we really wanted to use, or we want to learn or leverage the knowledge in a deep learning context that these models are able or capable to learn from different audit clients, right, without violating these data privacy regulations. So we also set up a framework that allows to learn. So for example, what we see here on the, from my side, I think, right side of the presentation is a federated learning setup where an autoencoder neural network is learned in a federated learning setup, and it starts to accumulate knowledge from different audit clients, and without actually getting access to the individual data of the clients, because all what the clients are doing is they are sending the models to a central trusted entity, like for example an audit firm, but the data, the proprietary data of the client still resides at the client side. And what the trusted entity, for example, the audit firm does is, for example, it's accumulating or aggregating all the information that it has and the weights and the biases and the parameters of the models. And once this aggregation step is done, the new model with the knowledge of all the clients is actually sent back to the individual clients, and they can use it. So this is the idea of federated learning. We enhanced it even further. We did a couple of experiments with non-identical distributed data sets. So to see, okay, to which extreme or what is the model convergence at a certain extreme level of non-IID distributional data. And we also added some concepts of differential privacy to even, for example, enhance the privacy of the model. For example, adding noise to the gradients, which is a little bit more technical idea, or perform, for example, gradient clipping. So these things are the ones that we applied. The interesting thing, based on our experimental results, and in order also to publish our results, we usually refer to publicly available data. And what we are utilizing to make also our research reproducible are actually data sets that have been published by certain cities throughout the United States or in the UK as part of their open data initiatives. So for example, what you see here are results for vendor payments, data sets that we have derived from the city of Philadelphia, the city of Chicago in the United States, but one data set as well from the city of Europe in the UK. So these data sets are publicly available, and we would like to invite you maybe to use some of the code that we developed and try it yourself and see maybe if you want to apply it for your purposes. But the interesting thing is what we saw here was really that once we increased, for example, the number of participating or collaborating clients in that learning setup, that significantly allows us to detect certain anomalies in the data set, especially global anomalies, which we refer to anomalies, that these are anomalies that are quite unusual for all the different entities that are participating in this learning setup. So that was quite exciting. So this collaborative learning helps in that regard. So this actually accumulated then, or in a research question where we asked ourselves, why can't we bring, or let's try to bring all these different learning techniques together and simulate in a continuous audit setting, for example, different data distribution shifts over clients, over time, in a self-supervised learning setup. And that's what we are currently doing. So we think about, or we developed an approach or a learning environment, for example, where we think about, we have a global audit firm, and this global audit firm always receives constantly new models from the different clients that collaborate in this learning process. And the audit firm actually is accumulating this information that is retained in the parameters of these models, and then send it back to the individual clients, and the clients can then use these models in order to use them for the different audit purposes or audit tasks. So that's the idea, for example, anomaly detection, representative audit sampling, or disentangling degenerative processes that are in the data. So we tried this as well with the 3 data sets that I mentioned. We injected global and local anomalies into the data sets, and we simulated certain distribution shifts and also IID and non-IID data settings. And the interesting thing was actually that with the continual learning setup or the continual federated learning setup, we really see that the models in their learning process, first of all, they behave much calmer. So we don't see these shocks as we see in the first illustration that we see on top, where the model, whenever there's a new data set coming, and the reconstruction error or the learning error actually really bumps up. So it's a much, much calmer learning. So it retains the knowledge that it's learning over time and over the different clients. And at the same time, it really helps significantly to improve for all of the different participating clients the anomaly detection performance. So we see a spark of the potential of this collaborative learning environment in a continual learning setup. So collaborating on training those foundational models over different clients is beneficial for all the different participating clients. One thing or two things that we're currently investigating and that we're working on as a future work is we want to, of course, investigate potential data poisoning attack scenarios because if one of the clients, for example, behaves in a malicious attitude or behavior. And the other thing that we are currently also investigating is the addition of techniques derived from differential privacy. So with that, thank you very much for your attention. And yeah, we are more than happy to discuss and answer potential questions that you have. Thanks a lot.
I actually have one question.
Okay, thank you. Thank you for your presentation. Yeah, let's open the floor for... Oh,
I actually have a question.
Yeah.
So when you're So which part exactly do you add in the human federation to the learning process?
Okay. Yeah. Maybe just very briefly we can go back to the slide. So if you speak about federated learning, actually what we have is we have these different federated clients. So and these individual clients, they have their proprietary data. And the individual clients, they train the models or their models based on the proprietary data, and they send the models back to a central server.
Oh,
and
I see. So you can adjust your base model.
Right, exactly. So,
thank you.
Okay, good, thanks.
any more questions in the audience? Yeah, I have a question there.
Sorry, it's probably something that I didn't really understand. It's from the beginning of the presentation. You said that most models are trained on single client data for a single date and a single task, yes, for looking for anomalies, I guess. Do they actually work? I mean, it seems quite difficult that a model trained on single client and single period data might actually work or work well at all. So
yeah, thanks very much for the question. I think that's a very relevant one. So when I speak about this, it's based on, if I think back about my time at PW Forensics, what we usually get is, for example, we go to a client, and the client has this latent feeling that maybe there's something going on within an organization. So what you could do, for example, is you can download all the journal entry data. And if you speak about a mid-sized company, or for example, a large, for example, German corporation, then we are easily in the million of journal entries that are generated by these organizations, right? And then we can take this data, for example, in an unsupervised deep learning setting, for example, using an autoencoder neural network, as we saw it here, and train this data to learn, for example, anomalies or to detect anomalies in an unsupervised learning setting without labels, basically. And, for example, based on the reconstruction error or based on the latent space distribution, detect, okay, are there, for example, unusual generative processes that yields to a high reconstruction error, or maybe they reside in a different location in this latent space. That's the scenario. And this is usually done maybe if you apply this to an audit setting, what you usually do is you download the data out of an SAP ERP system for the particular year that you are auditing, right? But usually you're not downloading the entire data from the last 10 years and train your model based on that, because that's far too computationally expensive and also too time consuming. But if you could, for example, each year bring your model that you have trained on the data from the previous year to your audit client, and then just continue to learn using the new data for the new fiscal year, that would be fantastic, because it's releasing you from maybe spending these additional researchers. That's the idea. But at the same time, you don't want to forget what you have learned maybe over the last 10 years, because maybe there might be a business process. We see this very often where there may be discontinued business processes that are then picked up again, because there's a lot of dynamics in organizational data as well, right? So that's the idea.
Yeah, we'll have one more question there.
Let's not say the logic of PwC. Let's assume that a CPA firm wants to develop a large language model and get competitive advantage on their competitors and create a unique way of auditing. Obviously, let's forget about all the obstacles of dealing with the standard setters, etc. What would you do?
Is it a question? Because
No?
Okay, perfect. Yeah, maybe we can go to, so how would I do it? Is that the question?
What would you do?
Yeah, of course. I mean, maybe coming back to the seminal paper of the Stanford University, I mean, we see here that first of all, they prepared and accumulated all the different data modalities that they have within an organization, similar to Bloomberg GPT. I think that's probably one of the first steps. So you need to have the foundation, the data, in order to train such a large language model. And this is actually, I think, a data engineering or a data pre-processing task that needs to be accomplished. Then, of course, as a next step, what you might want to do is to set up a self-supervised learning environment in order to learn such a model. And then the next step would be either via transfer learning or maybe human language-based fine-tuning to fine-tune these models for particular audit tasks. And that's actually one thing that we are currently working on also to a certain extent in one research project, where we're using, for example, ChatGPT and fine-tune it via natural language for particular audit tasks. Because these large language models, for example, like ChatGPT, they can also do anomaly detection on tabular data, right? And you can fine-tune those large language models with natural language in order to achieve that. So I can envision a future, maybe to answer the question a little bit more precisely, where an audit firm, or maybe one of the big audit firms, they have their own large language, or I would say foundational models, because large language models are just a subpart of these foundational models, which are specifically trained for the language purpose. But it could be the case that I think each of the big audit companies in the future, they have, from a competitive advantage perspective, foundational models available.
Okay, thank you.